Hello friends, I welcome you all to this fifth video on the series of group theory. This video is going to talk about subgroups. Come on, we will see what is meant by subgroup, its properties and a few problems. A subgroup is going to be one that satisfies the following. Let me consider a non-empty set H, which is going to be called as a subgroup of the given group G star if it satisfies all the properties of G with respect to the same binary operation, that is going to be closure, associative, existence of identity and inverse. So a non-empty subset, the word over here which is important, is going to be subset. What is H? Your G is going to be a bigger picture. This is going to be your G where you have your binary operation defined on its star. And now inside it I am going to find a subset which is going to be called as H, and you define the same binary operation star on the collection of elements of your H, and this collection of elements also satisfy the same properties of a group, namely closure, associative, identity element and inverse. You need to be careful that your identity element E is going to be unique, that is going to not have any replica. Hence the identity element of G and the subgroup or the subset H will always be the same. So this identity element E will always be a part of your H also. So how we can show that? Let us take an example and things can become much clear to us. Consider the set of your real numbers, and these are with respect to addition. I know that it is going to form a group. Now from the set of real numbers, the big picture with respect to addition, I am going to take one small subset of it called as the set of integers. The set of integers. And now the set of integers are something that contains 0, plus minus 1, plus minus 2 and so on. With respect to addition, I know that Z and plus again forms the group, which means it satisfies your closure, it satisfies the associative laws, that is I know that adding any three elements in the order is going to be the same. So associative law is going to be true. I know that the identity element exists. With respect to addition, 0 acts as the identity element and inverse exists for each element. So I have A, I have a minus A, that gives us back a 0. So all the properties of group are being satisfied by the subset also. So this subset will now be referred by the name subgroup. Now this subgroup can also have a interior subgroup. If I take the bigger picture as Z with respect to addition, I can say that NZ with respect to addition will be a subgroup for it. Say suppose my n is going to be equal to 2. So what will happen? Let me have Z with respect to plus, and the subset is going to be 2Z with respect to plus. What is going to be 2Z? 2Z is the collection of all integers that are going to be multiples of 2 or even numbers. 0 plus or minus 2 plus or minus 4 plus or minus 6 and so on. This 2Z with respect to plus will also form a group. Can we check? You take any two even numbers and then add the even numbers. When you add two even numbers, you have again a even number. So you know that the addition is going to satisfy the closure property. You take any three elements and then add them up in any order. It will again be an element of the same quantity. So this is going to be 6 plus 6, so 12, and they tally. So associative law is going to be true. I know that identity element 0 is a part of this even number set, integers, so identity element exists. With respect to 2, minus 2 is inverse. With respect to 4, minus 4 is inverse. And identity exists and inverse also exists. So all the properties of a group are satisfied. Hence I can call this 2Z with respect to addition is going to be a subgroup of which group? Your Z with respect to plus. Okay, so this is going to be the concept of subgroup. You have a bigger picture and the smaller picture also satisfies all the criteria with respect to the same binary operation. The keyword is same binary operation. Then the smaller picture or the smaller subset is now referred as your subgroup. Now we will check on few properties for subgroups. Property number 1 says that H, star, the subgroup of the group G star, is going to be a subgroup if and only if it is going to satisfy A star B inverse belongs to H for any A, B belonging to H. So I show that H is a subgroup. You have an if and only if, so it is a double-sided arrow. Whenever A, B belongs to H, your A star B inverse belongs to H. Now this is going to be a two-way communication like quantity. So the problem can or the property can also be stated as state and prove the necessary and sufficient condition for a subset of a group to be a subgroup. A subset, when will that subset of this G will become a group, subgroup? This will become a subgroup if it satisfies this criteria. So we will move on to see. If you are going to prove, then you will have to prove it in a two-way round quantity. Take your LHS, get your RHS, and vice versa way, take your RHS, get your LHS. Only then it will be satisfying the double-headed arrow, that is, it is satisfying if and only if condition. Coming to the first part of the proof, given G star is going to be a group, let me assume that H star is a subgroup. What I need to prove, if I am taking subgroup, I am assuming my LHS. Let me prove that RHS is going to be true. So when you are taking it to be a subgroup has all the properties of group to be true. So it satisfies closure, it satisfies associativity, it has identity element, and it has inverse. So when I pick any two elements A and B that belongs to H, I know that for the elements A and B that belong to H, every element has an inverse. Inverse elements exist. So what happens? B inverse also belongs to H. So whenever I have B belonging to H, B inverse also belongs to H by existence of inverse. And next, I know that I have two elements A that belong to H and B inverse that belong to H, and for my subgroup I know that closure law is true. What do you mean by closure law? Take any two elements belonging to the set. Now it is going to be H. The binary operation on it also have to belong to your H. That is what is closure. So closure is going to be true, in which case for these two elements A star B inverse also belongs to H by closure. So what we have proved finally, A star B inverse belongs to H. Where did we start? We started with H being a subgroup, and what did we prove? We proved A star B inverse belongs to H. Now moving in the vice versa way, what we are going to take or assume is that for any element A, B belonging to H, I assume that A star B inverse belongs to H. I need to show that closure, associative, identity and inverse are going to be true for the set which is going to be H. Come on, let's catch on with it one after the other. the converse part, we assume that A star B inverse belongs to H for any A comma B belonging to H. To prove H star is going to be subgroup. Now, let me have the existence of identity to be proved first. I have the element A belonging to H, and I know that for any element A comma A belonging to H, this condition, what does this say? A star A inverse belongs to H. But what do you know about A star A inverse? A star A inverse is nothing but your E. So E belongs to H. What is your E? E is the identity element. So identity element has now come inside my H. Now the second thing, let me go for existence of inverse. I have E that belongs to my H from my first condition over here, and I also have the element A that belongs to my H over here. So what does my condition say? Whenever A comma B belongs, A star B inverse belongs to H. A comma B belongs to H implies A star B inverse belongs to H. Now E belongs to H and A belongs to H will imply what? E star A inverse will belong to my H. What is going to be E star A inverse? E star A inverse is my A inverse. So your A inverse now belongs to your H, and now we have shown that for every element A, the unique A inverse also is there inside H. So identity element is there, inverse element is there. Now we move on to the next property, closure. Let B belong to H, and whenever we have an element B belonging to H, we have B inverse also belonging to H, that is by our existence of inverse. So B inverse belongs to my H. Now for any element A and B inverse that belongs to H, what does the property say? A star B inverse, the whole inverse belongs to H, because I know that for A comma B belonging to H, A star B inverse has to belong to H. So instead of B, if I am going to take B inverse, then B inverse, the whole inverse has to belong to H. What is B inverse, the whole inverse? It is nothing but our B. So A star B belongs to H. So whenever I pick A and B belonging to H, I have A star B belong to H, which means the operation of star is going to be closed, or closure is going to be true. When the closure is actually true for two elements, that can be extended for any number of elements like A into B into C or A star B star C. This can be shown to be the same as A star B star C. So from over here, your associative law can also be shown to be true. Thus, I have associative law, closure, identity and inverse to hold true. Therefore, what happens? From this part, I have shown all these things are going to be true. Therefore, H is going to be a subgroup. So, this is going to make the property number 1 to hold true. Now, moving on, we go to the second property, which says intersection of two subgroup is a subgroup, but union need not be a subgroup. So, from the bigger set G, I am going to have two subgroups, one called as my H1 and the other one called as my H2. Now this part is my intersection part. They say that this intersection is also a subgroup, intersection of two subgroup. This intersection part, which is nothing but my H1 intersection H2, this portion is also going to be a subgroup. But what they say is the bigger picture over here, by taking the union of the data, what is going to be the union of the data? So whenever we have the collection of two subsets, the union will be the element that is going to lie entirely in your A as well as in your B. So it is going to be your union. What they say over here is H1 union H2 need not be a subgroup, but the intersection portion will obviously be a subgroup. Come on, we will check how this happens now. Case 1. So we are going to show that intersection is going to be a subgroup. Let G be a group and H1 star and H2 star be two subgroups of your G. Just like what we have seen over here, the bigger picture is your G and the smaller picture, we have now two smaller copies of it called as one to be your H1 and the other one to be your H2. Now A comma B belong to H1 intersection H2. Let me pick, this is the quantity which is my intersection region, and let me pick two elements from over here and let me call them to be equal to A comma B. So I pick A comma B belonging to H1 intersection H2. I need to show that this part H1 intersection H2 is going to be a subgroup. Now from my property number 1, it's just clear that when I show that A star B inverse belongs to my H1 intersection H2, then the things will become clear because it is going to be a necessary and sufficient condition for proving it to be a subgroup. So this is going to be the idea. I pick two elements A and B from my intersection part, and since this two element is going to be, I have A, I have B. These two elements are part of my H1. If they are part of my H1, what happens? Whenever A comma B belongs to H1, A star B inverse also belongs to H1. That is going to be my property number 1. And whenever A comma B belongs to my H2, so this belongs over here, this A star B inverse also belongs to my H2. This is again by my law. So this A star B inverse belongs to your H1, also belongs to your H2. So A star B inverse belongs to H1 intersection H2. So we have shown that this is going to hold true, in which case I can just make sure that H1 intersection H2 is going to be a subgroup by my property number 1, which is nothing but the necessary and sufficient condition for any subset to form a subgroup. So what we have proved over here in this case, the intersection of two subgroup is going to be a subgroup. We have the second case left out, the union need not be a subgroup. So for this, let us now take a contradiction and then prove the quantity over here. Okay, so what is the contradiction I'm going to take is, let the bigger picture be Z with respect to addition. Now let this be taken to be your group G. I am finding two subgroups inside it. One of the subgroup is called as 2Z with respect to addition modulo addition operation. We already showed that this 2Z kind of quantity is going to form a subgroup. Not necessarily 2, you take nz, nb, any element of positive integer, that will again form a subgroup. So in which case over here I am going to now take one more copy which is called as the 3z. Okay, let me take it as 3z with respect to the same binary operation called as addition. So now what I need to do over here is, I am taking A to be the first subset, which is going to be 2z, that comprises of elements 0 plus minus 2 plus minus 4 plus minus 6 and so on. The second subset is going to be your 3z, 0 plus or minus 3 plus or minus 6 plus or minus 9, all the multiples of 3 will be over here. Now when you take the union of A and B, what will be A union B? The union of A and B will contain elements 0 plus or minus 2 plus or minus 3 plus or minus 4, which are nothing but elements of A as well as elements of B, all of them put together. So plus or minus 6 plus or minus 9 and so on. The combination of all, both your first and the second set, will come inside your union. Now let me pick two elements from over here. 2 which is belonging to A union B. There is a 3 that also belongs to A union B. 2 belongs to A union B and 3 also belongs to A union B. Now if it is going to be a subgroup, then all the properties of group have to be satisfied. First thing to be satisfied is going to be closure. What do you mean by closure? The binary operation has to, whenever you have A comma B belonging to your G, your A star B must also belong to G. The binary operation over here is going to be addition. So what will happen to 2 plus 3? 2 plus 3 is going to be 5. But do I find a 5 over here in this combination? No, I have plus minus 2, plus minus 3, plus minus 4, and then comes plus minus 6. 5 is not a multiple of 2, neither it is a multiple of 3. So 5 doesn't belong to A union B. So closure property itself is getting violated. So can it form a subgroup? No, it need not have to form a subgroup. So we conclude that union of two subgroups need not be a subgroup, but when you take the intersection of them, intersection for sure will form a subgroup. I hope the concept of subgroup and the properties of subgroup are going to be clear from this video. Happy learning, keep learning.